Okay, so real quick, before we start the video, I forgot to mention that I would recommend for these following questions that you try to use each of the 11 tests at least once. In my explanations, I do use all of them at least once, so I would recommend that you do the same to make sure you're getting experience to all of the types of questions you might be asked on the AP exam. Okay, now on to the video. Alright, so the problem solving video for Unit 9 Part 1. So for this video, I've compiled a bunch of different series that are of varying difficulty, so there's something in this video for everyone. So we'll be going through a bunch of different series, like I said, and we're going to be trying to find out if they converge or diverge, and it's going to be a little bit of extra stuff thrown in there for fun. Okay, so to start off with, we need to have these 6 series here, and we need to determine whether they converge or diverge. If they converge, find the sum. Okay, so for all of these, if they converge, we're going to be able to find the sum for these. Okay, so we'll start with the first one here. The sum from n equals 1 to infinity of negative 2/9 to the n. So this is a geometric series. And if you remember, a geometric series converges when the stuff that's in here, if you take the absolute value of it, it's less than 1. So this is the common ratio, we call it. So if we take the absolute value of the common ratio, which in this case is negative 2/9, that common ratio is going to be less than 1. If this is true, then the series converges. So in this case, the absolute value of negative 2/9 is 2/9, which is less than 1, so our series does converge. Now the question is, what does it converge to? And for that, we have a formula. So we're going to use the formula for the sum of an infinite geometric series, which is a1 over 1 minus r. What is a1? What is r? a1 is the first term in the series. So since we're starting at n equals 1, we're going to be plugging in n equals 1 here, which will give us the first term, our a1. R is the common ratio, which we said before is negative 2/9. Okay, so let's do the stuff, and we will get a1. If we plug in 1 into here, we'll get negative 2/9 for the first term. So negative 2/9 like that, over, and then 1 minus, the common ratio is negative 2/9. So if we subtract that, we'll be adding 2/9 like that. Okay, and then now to simplify this a bit further, we'll turn this into 9 over 9. So it's negative 2 over 9 over 9 over 9 plus 2 over 9. All the 9's will cancel in the denominators, which will get us negative 2 over 11 for the sum of that series. Okay, let me erase this real quick. Alright, so the next series will be moving from left to right and then down, so we'll be looking at the series next. So in this series, we're starting at n equals 4 and we're going to infinity, and we have this here. So this does not look like a geometric series, you'll notice. So our strategy here is going to be, okay, so since we know the series converges, and since we know if the series converges, we're going to find the sum of it, well, that gives us kind of a hint that this is going to be a telescoping series. And another hint is this can be split up by partial fraction decomposition, like we're going to do in a moment, which will give us a fraction and then another fraction. So that's another clue that we're dealing with telescoping series here. Excuse me. So the first step here is going to be to split this into fraction minus fraction, like I said. So we're going to have to first of all factor the denominator. If we do that, we will get the sum from n equals 4 to infinity of 10 over, okay, factoring this gives us n minus 3 and n minus 1, like so. Okay, now we're going to use a very neat trick that you can read about if you don't know, but if you do know, we're going to use it. So we're splitting it up into two different things, right? One thing will have a denominator of n minus 3, and the second thing will have a denominator of n minus 1, and then we'll have two constants, or two constants a and b. Okay, so the way we're going to figure it out what a and b are is you'll notice that here, if you plug in, so for a, if you plug in n equals 3, that's going to cause the denominator to be 0, right? So n equals 3 will make this 0. So we'll go up here, ignore the n equals 3, and plug in 3 into the rest. So we'll have 10 over 3 minus 1, which is 10 over 2, which is 5. That value is the value of a. So a equals 5. Likewise, we can do the exact same thing for b. So b, you notice that n equals 1 makes this denominator 0. So we'll go up here, ignore the n minus 1, and plug in n equals 1 to the rest. So that's 10 over 1 minus 3. That's 10 over negative 2, which is negative 5, right? Find the values for a and b. Let's form this series. So we have the sum from n equals 4 to infinity of 5 over n minus 3 minus 5 over n minus 1. And we do have the form of a fraction minus a fraction, so this is going to be a telescoping series. So remember, the way we solve telescoping series is we just start out by listing all the terms. Oh, whoa, went way too far. Okay. So we're just going to list out all the terms, and we're going to watch as everything magically cancels in front of our eyes. So as we just start by plugging in n equals 4 into each of these, we'll get 5 over 1 minus 5 over 3. And now you're just going to have to watch me do a bunch of pretty simple stuff here. 5 over 2, 5 over 4. You'll notice there's a pattern, right? The denominators are growing at a consistent rate. Minus 5 over 5 plus 5 over 4 minus 5 over 6. And we can go on and on and on and on, but I'm just going to end it off by saying, okay, we're going to go forever and ever, and eventually we're going to get to, if we plug in n minus 2, for example, we will get 5 over n minus 2 minus 3, or n minus 5, minus 5 over n minus 3, plus, and then 5 over n minus 4, 5 over n minus 2, and finally, to finish us off, 5 over n minus 3, minus 5 over n minus 1. And that is the final term of our series, or infinite series, right? So now let's look at everything magically cancel, like I said, right? So see the 5 over 3 here is a negative 5 over 3. Here's a positive 5 over 3. So this is going to cancel with that. And then let's see what else do we have. We have a 5 over 4 here. It's going to cancel with this 5 over 4. So this cancels with here. This 5 over 5 is going to cancel with the next term here. And then same thing with the 5 over 6. Okay, so you notice this guy survived, everything else is dead. Now what about the ending? This is going to cancel with something previous. This n over 3 is going to cancel with this n over 3, n minus 3. And then this n minus 4 is going to cancel with the n minus 4 that came previously. And then we are left with the n minus 2 and the n minus 1. Okay, so now remember, after we did all that, all we got to do is we got to take the limit of this leftover, the stuff that survived the purge. We're going to take the limit of it as it approaches infinity, as n approaches infinity. So the limit as n approaches infinity of, what do we have left? We have 5 plus 5 halves minus 5 over n minus 2 minus 5 over n minus 1, which is 5 plus 5 halves, or 15 halves. So this series does converge by the telescoping series test. Next one, right? This guy right here. This is a very, very simple one. It looks very similar to this. So it is a geometric series. I remember earlier on I said, if the common ratio, or the stuff that's inside the parentheses, is greater than, the absolute value of that is greater than 1, then the series is going to diverge, or else it's going to converge. If it's greater than or equal to 1, it's going to diverge, otherwise it's going to converge. So in this case, we have 3 halves, and the absolute value of 3 halves, which is 3 halves, is greater than 1. Is greater than 1 means that the series is going to diverge by the geometric series test, okay? I don't even need to pause to erase because that was really, really quick. The fourth one, we have 3 to the n over n squared. So notice right now, if we were to plug in infinity, if you will, we'd get 3 to the infinity over n, or infinity squared, which would be infinity over infinity, which is kind of giving us a clue that we might want to consider the nth term test. Because if we use L'Hopital's rule, we might eventually get that into something that is not infinity over infinity. Okay, so we're dealing with the sum from n equals 1 to infinity of 3 to the n over n squared. And the way we're going to do this is we're going to take the limit as n approaches infinity of this stuff here. Like we said, this goes to infinity over infinity. So we're going to use L'Hopital's rule to give us that the limit is equal to the limit of n approaches infinity of, take the derivative of the top, take the derivative of the bottom. This is going to be 3 to the n times the natural log of 3 over 2n. Okay, that's not working very well, because if we plug this in, we'll still get infinity over infinity. Fear not, we can use L'Hopital's rule again. The limit as n approaches infinity Okay, if we do one more time, we will get 3 to the n times the natural log squared of 3 over 2. And now, finally, we do not get infinity over infinity, we just get infinity, which means that this series diverges by the nth term test because infinity is not equal to uh, 0. Okay, so that is that. Now let's look at the Alright, the fifth one. So we have the this one. It doesn't immediately pop out to us whether what kind of test we should be thinking about using here. Okay, but actually, since we have a similar kind of exponent here, we can kind of consider trying to combine this into one thing raised to the something relating to n power. So this is actually going to be a geometric series in that way. So we want to try to get these to have the same exponent. Okay, so the first thing we'll do is we will flip them so that the n will come to the front of this part. So if we do that, and we bring the -6 down and the 8 up, we'll get 8 to the n minus 2 over -6 to the n minus 3. Okay, and now we can use one of the powers of exponents that makes life easier for us. We can split this thing into two different pieces. Okay, we can split this 8n minus 2. We can split that into 8n minus 1 times 8 to the -1. That does not look like an arrow. Now it does. And similarly, we can split this into -6 to the n minus 2 and -6 to the, oh, not n minus 2, forgive me. Negative n minus 1, and then -6 to the -2, like that. Okay, so if we do that, we will get 8 to the n minus 1 times 8 to the -1 over -6 to the n minus 1 times -6 to the -2, which is, let's see, we can bring this -6 up, we can bring this 8 down, we'll get 36 over 8, and then we'll have 8 to the n minus 1 over -6 to the n minus 1. Okay, now it should be clear that this is indeed a geometric series. So 36 over 8. If we combine this into one thing, we'll get 8 over -6, which is -4/3, n minus 1. And then if you, again, think about what makes a geometric series converge and what makes it diverge, it's all because of this common ratio and the absolute value of it. So the absolute value of -4/3 in our case is 4/3, which is greater than 0, which is greater than 1. So that means the series is going to diverge by the geometric series test. Okay, so the last one is very, very simple. It is the sum from 1 to infinity of e to the e divided by n. Key thing here, e to the e is a constant, so it can be pulled out of the summation completely, giving us e to the e times the sum from n equals 1 to infinity of 1 over n. This is the harmonic series. It diverges, that is it. So we would just say, okay, well, the series diverges by the harmonic series test. Okay, that was the end of the first question. So for the second question, we have 3 series, and we have to use the integral test to determine if the series converge or diverge, and we need to check our work with another test. Okay, so we have to use the integral test every single time. So when you look at this first series, and your brain is screaming to you, P-series test, you have to ignore what your brain says and use the integral test first. We'll use the P-series test later to check our work, but for now we do need to use the integral test here. So if I were to call this stuff inside a function, I'll say y equals 1 over x to the 5th. I need to ask myself 3 things about this function before I can even think about applying the integral test. First, is it positive? Second, is it continuous? And third, is it decreasing? Is this always positive? Yeah. Is it always continuous? For x is greater than 1, that's key. For x is greater than 1. And for that, it is. And is it always decreasing? Well, this is going to keep getting bigger, so it is going to keep decreasing. So yes, all the conditions are met, so we can use the integral test. Remember what the integral test says. I will move down to the bottom here. The integral test says that if we can apply the integral test, well, we can take the indefinite integral, so we'll take the limit as b approaches infinity of the integral from 1 to b of the stuff inside. In this case, it's 1 over x to the 5th dx. And whatever this does, our sum will do the same. If our integral diverges, so will the sum. If it converges, so will the sum. So we need to work on evaluating this indefinite integral. So the way we will do that is as follows. So first we'll write this as x to the negative 5. So x to the negative 5 dx, 1 and b. And then so we will increase this by 1, so we'll get negative 4, and then divide by that. So we'll be dividing by negative 4 as well. We'll have x to the negative 4 over negative 4 going from 1 to b. So that's going to be the limit as b approaches infinity of, before I plug in the numbers, I'm going to rearrange this. I'm going to take this x to the negative 4, bring it down to the bottom to make our lives a little bit simpler to clearly see what's going on. So that's negative 4x to the 4th from 1 to b. If I plug that in, I will get the limit as b approaches infinity of 1 over negative 4b to the 4th minus negative 1/4. So it's going to be plus 1/4. And as b approaches infinity, this guy is going to go to 0. It's going to go away, and we're just left with 1/4. Remember, key thing for the integral test, this is not your answer. Your sum does not necessarily converge to 1/4. All we know is that it converges to some number. Since the integral converges, so does our series, okay? So we'll say that our series converges by the integral test since the integral converges. And now we need to check this with a p-series to make sure that we did this right. Okay, so now we need to check our answer with the p-series. So remember, the p-series says that if we have one or some constant over n to an exponent, if this exponent is greater than 1, the series is going to converge. If it is equal to 1, it's the harmonic series, it'll diverge. If it's less than 1, it's still going to diverge. So in our case, it is 5. It's greater than 1. We can say, since 5 is greater than 1, by the p-series test, our series will converge. That was a million times faster than the integral test. Why didn't we just use it in the first place? Because the question said so. You can't argue with the test, okay? Okay, for the next one, we have the integral from, not the integral, the sum from n equals 1 to infinity of 1 over n squared plus 1. We are going to use the integral tester, but first we have to check the conditions. Is it positive? It looks to be positive. Is it continuous for n is greater than 1? It is continuous. And is it decreasing? It is. So we're going to call the function y equals 1 over x squared plus 1. We're going to write the conditions. Okay, it meets all the conditions. So we're going to use the integral test here. So we're going to take the indefinite integral, so the limit as b approaches infinity of the integral from 1 to b of 1 over x squared plus 1. And if you didn't get this integral in 5 seconds, I'm ashamed of you. It is the arctangent function. So it's the limit as b approaches infinity of the arctan. That's not how you spell arctan. That's how you spell cartan. So it is the arctan of x from 1 to b. I'll move over here. Is the, if we plug in our stuff now, we'll get the limit of the arctan of b minus the arctan of 1, like that. What is this? Okay, well, let's see. Arctan of b, as b approaches infinity, is the horizontal asymptote at pi equals 2, so that's that. And then the arctan of 1 is pi over 4, so our integral is equal to pi over 4. Remember, again, this is not the answer to the series itself. We just know that since this converges, so does the series. So we'll say, since the integral converges, again, the series is going to converge by the integral test. Okay, now we need to check our work using a different test. For this, I'm going to use the direct comparison test. I'm going to compare it to 1 over n squared. So we're comparing this to the sum from n equals 1 to infinity of 1 over n squared. This is a p-series. It converges. Okay? Now what we can do is we can say, all right, since this converges, if I want this to converge too, this stuff in here needs to be less than 1 over n squared. So the question is 1 over n squared plus 1 always less than 1 over n squared? We'll cross multiply, we'll get n squared is less than n squared plus 1. Subtract n squared from both sides, you get 0 less than 1. That is true. So we have a true statement. The direct comparison test will tell us that, okay, since this series converged, so does this one. So we have checked our work. Our integral test told us that the series converges as well. So we're done. Let's move on to the third part. Third part, we have a very simple looking thing from 1 to infinity of n to the negative 1/2. Let's rewrite that first. So this is going to be equal to sum n equals 1 to infinity of 1 over the square root of n. Okay. Now, does this meet our three conditions? If we have a function y equals 1 over square root of x, does this meet our three conditions? Is it positive? Yes. Is it decreasing? Yes. Is it continuous? Yes. So it meets our three conditions. We can use the integral test. Okay. So let me do that here. So we'll have the indefinite integral from 1 to b of, I'm going to use this form because it's easier to integrate with than 1 over square root of x. So if we do this, we will get, remember, so we're going to add 1 to this and multiply by the reciprocal, right? So we're adding 1 to negative 1/2. That will get us a positive 1/2. And we're going to multiply by the reciprocals. We're going to multiply by 2. It's going to be 2x to the 1/2 from 1 to b. Oh, actually, very important. Let me keep the limit. You don't want to skip the limit. That's important. b of where were we at? 2 square root of x, or 2x to the 1/2. Remember, x to the 1/2 is the same as square root. So from 1 to b. Now if we plug in our thing, it's going to get us 2 square root of b minus 2 square root of 1. If we put in larger and larger numbers, this is going to grow and grow and grow forever. So this limit is equal to infinity. So we have said, okay, this integral diverges. So that means that the series diverges as well. Okay, how are we going to prove this? Well, we're going to use the p series again. This is a, remember, this is a, I can rewrite this as 1 over n to the 1/2. And since this 1/2 is less than 1, we can use our p series test and say that this series will indeed diverge. Okay, so that was question 2. Let's move on to question 3. Alright, so in question 3, now we can use whichever tests we want, so we're not constricted to using just the integral test. So let's see what we can do. So in this first question, we have the sum from n equals 1 to infinity of 4 plus 3 to the n over 2 to the n. So to me, this looks very similar to just 3 to the n over 2 to the n, so I'm going to compare it to that and maybe use one of the two comparison tests. So we're going to be summing from n equals 1 to infinity of 3 to the n over 2 to the n. This is what I'm comparing it to. I'm comparing this series to this one. So I can say that's 3/2 to the n, and this should look very similar to a divergent geometric series because the common ratio inside is greater than 1. So I can say, alright, this diverges by the geometric series test. So all I need to do now is I need to prove that 4 plus 3 to the n over 2 to the n is greater than 3 to the n over 2 to the n. So 4 plus 3 to the n over 2 to the n is greater than 3 to the n over 2 to the n. And it's greater than because this series diverged. If it was convergent, then we'd be proving that this is less than this. But since this is a divergent, we want to prove that it's greater. So now let's see, we cancel these out. So we'll have 4 plus 3 to the n is greater than 3 to the n. And then these will cancel, and we'll have 4 is greater than 0, which I believe, I'm 50% sure that that is true. So, okay, so now it's a true statement. So now we can conclusively state that the series up here, it diverges by the direct comparison test. Okay, so second one, the sum from n equals 1 to infinity of e to the 2n over n. So this looks to me like I want to use the nth term test, since I can see that I don't get 0 right away. I'm going to take the limit. So what I want to do is I want to take the limit as n approaches infinity of this stuff. So e to the 2n divided by n. And if I do that, I will get infinity over infinity. So this is a incomplete form, so I'm going to use L'Hopital's rule to help me simplify this limit a bit more. So if we do that, we will use L'Hopital's rule and get that this is equal to the limit as n approaches infinity of the derivative of the top, which is 2e to the 2n, over the derivative of the bottom, which is just 1. So now we have infinity over 1, which is infinity. Okay, so since our limit by using the nth term test is not equal to 0, the limit isn't equal to 0, we can say that the series will diverge by the nth term test. Okay, so finally, this series here, we have the sum from 1 equals infinity of the natural log of 2n plus 1 over n plus 1. So I'm going to again use the nth term test, because this again does not immediately give us 0 when we take the limit. So the limit as n approaches infinity of the natural log of 2n plus 1 over n plus 1. And now the nice thing about the natural log function is I can just take this limit and move it inside. So that'll give me the natural log of the limit as n approaches infinity of 2n plus 1 over n plus 1. So since the powers are the same for the n's, I'll be looking at the coefficients. So we have 2 here, we have a 1 here. That means that the natural log of 2, right? It's going to be the ratio of the coefficients, 2 over 1. So the natural log of 2, and this is not equal to 0. Okay, so this limit is not equal to 0, so that means our series will diverge by the nth term test again. Okay, so notice for the next two series here, they're not given to us in the normal form, so we're going to have to put them in there ourselves. So let's look at this first one. We have 1 over the natural log of 2 squared, 1 over the natural log of 3 cubed, 1 over the natural log of 4 to the 4th, and so on and so on. So if we wanted to write this in our sigma notation, notice we're starting with n equals 2 here. N equals 2 to infinity. And then what's inside the sum, we have 1 over the natural log of n raised to the n, right? So this is what we're trying to figure out. And since 1 to the n is equal to 1, I can rewrite the sum like this, just to make it a bit clearer what test we're going to use. Like that. This step isn't required, but it just helps me more clearly see what I'm doing. And this, since we have something, the whole thing being raised to the nth power, that's a good indicator that I want to be using the root test here. So with the root test, remember, we take the nth root of it and take the limit as n goes to infinity. So that's going to be the limit as n approaches infinity of the nth root of 1 over the natural log of n, all being raised to the n. So then this is going to cancel with that, which is the whole point of the root test, to get those things to cancel. And we'll be left with just 1 over the natural log of n, and as n approaches infinity, this will approach infinity. So we also have 1 over infinity, which is 0. Okay, so basically what the root test says is if our limit is greater than 1, then we have a divergent series. If our limit is less than 1, it's a convergent series. And since this is 0, which is less than 1, we have a convergent series. Okay, so we'll say our series converges by the root test since it is less than 1. The limit is less than 1. Okay, so for this final one down here, this is absolutely one of my favorite series to do. It's just like, it's so cool. You just see this magical result seemingly just appear out of nowhere. I really love it. So let's look at it. Okay, we have before we start solving, let's examine the series first. We have 3 to the 1 times 1 factorial over 1, 3 to the 2 times 2 factorial over 2 to the 2, 3 to the 3 times 3 factorial over 3 to the 3, and so on, so on, so on. So, and they even gave us the general form, 3 to the n times n factorial over n to the n. That's a lot of n's. So let me write that down. We have the sum from n equals, and it looks like we're n equals 1, so n equals 1 to infinity, of 3 to the n times n factorial over n to the n. So when you think about what series to use here, the key giveaway here is this factorial, and that's going to usually tell you that we want to use the ratio test here. Okay, so let's try solving this using the ratio test. I'm going to scroll down a bit because we're going to need a bit of horizontal real estate. Okay, so we're going to be taking the limit here, and remember the ratio test says that we're taking the limit of the n plus 1th term divided by the nth term, right? So we'll be taking the limit of the n plus 1th term, which is, I'll just take here and replace all the n's with n plus 1s. So 3 to the n plus 1 factorial over n plus 1 to the n plus 1. And then I'll be dividing that by the nth term. 3 to the n factorial over n to the n. So this is quite the limit, isn't it? Let's see what we can do to simplify this a bit, okay? First, instead of dividing it, let's treat it like multiplying by the reciprocal. So we'll have 3 to the n plus 1 times n plus 1 factorial over n plus 1 to the n plus 1. And then we'll be multiplying it by n to the n over 3 to the n factorial, okay? And now we're going to simplify this using just the normal powers of x, using the normal rules for the powers and the factorials and such, okay? So this is the limit as n approaches infinity of, okay, so how do we simplify the 3 to the n plus 1? Well, I can split this up, and I can split it up into 3 and 3 to the n, like that. How do I split up the n plus 1 factorial? I can split it up into the n plus 1 times n factorial, like that. And then how do I split up this? I can split it up into n plus 1 times n plus 1 to the n, like that. And then this I'll just leave it as is, because it is quite simplified already. And you'll notice that we have some things begin to cancel here. So we have the, we have the n factorial canceling there. We have the 3 to the n canceling there. We have the n plus 1 canceling within the first limit, the first part of the limit. So this simplifies to the limit as n approaches infinity of 3 times n to the n over n plus 1 to the n, okay? Now this is all, even if I just gave you this limit, this would be a little bit of a tricky one to evaluate. So let's see how we can do it. Okay, so I can pull out the 3 first. So 3 times the limit of n to the n over n plus 1 to the n. And then I can combine these two into one thing, since they both have the same exponent of n. So n over n plus 1 to the n. Okay, so now here's where the magic starts to happen here. I'm going to remind you of a little something. Okay? I'm going to remind you of a certain, nope, not like that. I'm going to remind you of a certain limit that you may have seen before. This limit here. You'll notice that our thing here, or n over n plus 1 to the n, this looks kind of, actually hang on, I wrote this wrong. Let me fix that real quick. So this should be like that. No, my bad. So anyways, we have this limit here, and notice how this limit and this limit look kind of similar, don't they? So we want to try to get this into this form. Alright, and the way we're going to do this, oops, I want to be in white. The way we're going to do this is by first we're going to flip this so the n plus 1 is on top. Okay, and when we flip it so the n plus 1 is on top, we're going to be also, remember, we're going to be taking the reciprocal of it, sort of. So it's going to be on the bottom, like that, of n plus 1 over n to the n, like that. Okay, so we kind of flipped it twice, if you will. So this, we can split this this fraction into 2, so we'll get n over n plus 1 over n to the n, and then this guy here, n over n, simplifies to just 1, so I'll replace that with 1. So, and now we have our limit. 1 over 1 plus n equals e. So this is equal to 3 over e. Okay, and now remember what the ratio test says. If this limit is greater than 1, it diverges. If it's less than 1, it converges. If it's 1, we don't know. 3 over e, remember e is a little bit less than 3, so 3 over e is going to be greater than 1. Okay, so since 3 over e is greater than 1, we said that our series diverges by the ratio test. Okay, that was a really fun problem. Now let's look at the fourth question. Alright, fourth question. So we have let a sub n equals 1 over square root of n plus 4. Determine whether the following series converge or diverge. And you'll notice that I marked this off in red saying you don't need to do it, because I realized that this and this are pretty much the exact same thing, just with this added on. Doesn't really make a difference to the problem. So I just told you to not waste your time with that. Anyway, so let's look at this. So we want to find whether this series converges, right? So square root, or not square root, sum from 1 to infinity of 1 over square root of n plus 4. Okay, so how are we going to approach this? Well, this looks similar to the series from n equals 1 to infinity of 1 over square root of n. So I'm going to use one of the comparison tests and compare it to this. So this is square root, why do you keep saying square root? It's 1 over n to the 1/2, right? Which is, by the p-series test, we'll say this diverges because 1/2 is less than 1. Okay, so this diverges by the p-series test. So we need to prove that this is greater than this. So we'll prove that 1 over square root of n plus 4 is greater than 1 over square root of n. Right? If this is true, then we'll say, okay, our series will diverge by the direct comparison test, right? So cross multiplying, we'll get square root of n greater than square root of n plus 4. Cancel, cancel. 0 is greater than 4. Hold on a second. Something's wrong, right? This doesn't work. We can't use the direct comparison test here because it will fail. Great. So now what are we going to do? Do we just waste that time doing this? No, we do not, because we can use the limit comparison test. That's the little trick. So let's use the limit comparison test here. And the limit comparison test says we take the limit as n approaches infinity of the unknown series over the known series. This is our unknown series. This is our known series. And we know whether this converges. We don't know whether this converges. So we're taking the limit of the unknown one divided by the known one. I can rearrange this to make it a little bit easier to see, easier to understand. Square root of n over square root of n plus 4. And I have the same power, so I can look at the coefficients. It's going to be the coefficient of 1 divided by 1, which is 1. So what this tells us in the limit comparison test, if our limit is a positive finite number, so it's it's any positive number that is a finite number, I guess. Yeah, I don't know what else to say. So if it's a positive finite number, it will pass the test, and this does pass the test. So what this means is that our series will do the same thing as our known series does. And since we said our known series diverges, our unknown series is going to diverge too, since it passed the limit comparison test. So we'll say, all right, this series here is going to diverge by the limit comparison test. Okay, so the next one, we have the same thing, but we were adding a little cosine pi n onto the end. Cosine pi n. What is the cosine pi n really doing? So if you plug in a bunch of different increasing values of n, plug in n equals 1, n equals 2, n equals 3, so on and so forth, you'll notice a little pattern. And the pattern is that this alternates between -1 and 1. So in that case, it's almost kind of like a -1 to the n that you'll see in the beginning of a lot of alternating series, right? So it's actually, I can actually rewrite this as n equals 1 to infinity of -1 to the, let's see, is it n or n plus 1? If I plug in 1 here, I'll get cosine of n, cosine of pi, which is -1, so I'll have -1 to the n here, and then a to the n, right? That looks good. So this series is -1 to the n times 1 over square root of n plus 4. Okay, so we need to check that this part of the series, the part that does not have the negative part associated with it, we need to make sure that this meets 3 major conditions, and then we can make a conclusion based on the alternating series test. So we will have 3 things to say about this. We'll think about 1, is it positive? 2, is it decreasing? Is it getting smaller? And then 3, does it fail the nth term? Okay, so let's think, is it positive? Yeah, it's going to be always positive, right? Positive over positive is positive. Is it decreasing? Yeah, because the denominator is going to get bigger and bigger. And does it fail the nth term? Yes, it does, because the n is in the bottom. Okay, so we're good there. It meets our 3 conditions, so we can say that this series is going to converge by the alternating series test. Okay, so for the final part, we have sine squared of pi to the n. So if you caught on to what we were doing with the cosine of pi to the n, the sine of pi to the n is going to be pretty much the exact opposite of that. notice how when we plug in values of n into cosine, the value is going to bounce between 1 and -1 forever and ever. But here with the sine squared pi of n, it's going to bounce between 0 and 0 and 0 and 0 and 0. So this is always going to be 0 for any multiple of pi, right? So 2 pi, 3 pi, whatever, it's going to be 0. So since we're only putting in numbers, positive whole numbers here, it's just going to keep spitting out zeros. So basically, this entire part of the series is just going to be gone. It's just going to reduce to 0. So this series, right, is basically the same thing as from n equals 1 to infinity of n. And you can use probably about every single test you can think of to evaluate this series. I'll use the nth term just for fun. The limit as n equals infinity of n equals infinity. So we have a divergent series by the nth term test. Okay. So now let's look at the next question on the list. Alright, so in this question, we have to determine if the following series are going to converge, absolutely converge conditionally, or just diverge. So first, we'll use the alternating series test on the series to see if it passes, okay? So on this first series, we'll have the sum from n equals 1 to infinity. And remember, when we're using the alternating series test, we're ignoring the -1 part. We'll have that. And then we need to make sure if it meets 3 conditions. First, it has to be positive. Second, it has to be decreasing. And third, it has to fail the nth term test. So the limit as n goes to infinity has to equal 0. Okay? So does our series here meet those 3 conditions? Let's see, is it positive for n greater than or equal to 1? Yeah, it is. Is it decreasing? Well, we have a bigger, the denominator is going to keep getting bigger, so yep. And then is the limit 0? Absolutely. So we've met those 3 conditions, and so that means this series will converge by this series up here is going to converge by the alternating series test. But does it converge absolutely, or does it converge conditionally, right? That's the question. So for that, we're going to look at just this series here. Let me erase the rest. So we're going to look at just this series. We're going to ignore this one, and we're going to ask us, does this series on its own converge, right? So we want to figure out, does this converge? We're going to have to use a different test. Okay, so in this case, I'm going to use the comparison test. I'm going to compare to 1 over n cubed. So I'll be comparing this to 1 over n cubed, which converges because it's the p series. So now I need to prove that this series is smaller than this one. So proving 1 over n cubed plus 1 is less than 1 over n. Okay, and then when I cross multiply, n is less than n cubed. N cubed is less than n cubed plus 1, so 0 is less than 1. This is true, so that means we have a this series on its own will also converge. So since this series converges and this series converges, we have absolute convergence. Okay. All right. In the next one, we have -1 to the n minus 3 over square root of n. So we're going to do the exact same thing we did before. We're going to look at just this part and ask whether it meets the 3 conditions. Is it positive? Is it decreasing? And does the limit equal 0? Let's see, is it positive? Yes, it is. Is it decreasing? Yes, it is. Is the limit 0? Yes, it is. So we met these 3 conditions, and we can say that the series in the top right will converge based on the alternating series test. So now we need to ask ourselves, okay, is it a absolute convergence or is it a conditional convergence? How are we going to do that? Well, we'll look at just this series and see whether it converges without thinking about whether the series up there converges. So looking at this, when I figure does this converge or not, I'm going to use a p series because that's the most simple series to use in this scenario. This is n to the 1/2, and since 1/2 is less than 1, this series is going to diverge based on the p series test. So since this series up here converges based on the alternating series test. This series down here diverges based on the p-series test. The -1 part is necessary to have the series converge. So we say it converges conditionally. It's conditionally convergent. Okay, I'll look at the final question. Question 6. For what values of x does the series converge? Find the sum of the series and write that as in terms of x. Okay, so they're asking what values of x does the series converge. So there must be like some limit on what x values we can input into the series for it to converge. So I'm guessing if we put a number outside of the range, of the OK range, then the series will diverge. Okay, so the first step, I think, it was going on in my mind, is I want both of these terms to have the same exponent. So I want these both to be raised to the same power. I want them both raised to the n power. So what I'll do is I will try to get these both in terms of n. Okay, so it's easy to do that for the x to the 3n. That's just going to be x cubed to the n. But this guy is going to be a little bit more work, just a tad. Okay, so what I'm doing right now first is I will bring this to the bottom, the 7 to the bottom, and that will allow me to bring the n to the front. Like that. And if you're not comfortable with what I did, remember this is just kind of having like x to the 2 being equal to 1 over x to the -2, right? That's the same idea here. 7 to the 1 minus n is 1 over 7 to the n minus 1. Okay, so this series, and we can split this up using our properties of exponents. We'll still have this, and so I can split this up into 7 to the n, and then 7 to the -1. And the 7 to the -1 is a constant that I can just pull out. Or wait, let me leave some space there. So 1 over 7 to the -1 times the sum from n equals 1 to infinity of x cubed to the n over 7 to the n. And this is going to keep bothering me unless I fix it. 7 to the -1, 1 over 7 to the -1 is just equal to 7 by the same property that we discussed up here. So we have this, and then since these are both being raised to the power of n, we can do what we've been wanting to do for the whole problem, which was rewrite it like this. Okay, now this is a lot more easy to think about. We're asking for what values of x does this series converge? And well, this is a geometric series, right? This will converge if the ratio, which is the stuff inside here, is the absolute value of it is less than 1, right? So the absolute value of our common ratio has to be less than 1. And remember, x is not really a variable here, it's a constant. So don't think like you're doing anything really, really fancy here. X is just a constant. So we want to make sure, we want to figure out well, for what values of x is this absolute value less than 1, like we have here. So I can rewrite this as -7, or I'll take it step by step. I'll say -1 is less than x cubed over 7 is less than 1. And then I can multiply by 7. I'll get -7 is less than x cubed is less than 7. And then I'll take the cube root, and I will get that the cube root of -7 is less than x is less than the cube root of +7. So if the x value in here, if the x value here is anywhere in between the cube root of -7 and the cube root of +7, then the series will converge, or else it's going to diverge. Okay, so now we need to find the sum of the series. How do we do that? We can use the formula for the infinite sum of a geometric series, a1 over 1 minus r. That's the ugliest r I've ever seen. There we go. So a1 is the first term, right? That's what's going to happen when you plug in 1 into here. So if we plug in 1 into n, we'll get, so the first will be x to the 3 times 1 times 7 to the 1 minus 1, 7 to the 0, so it just goes away. And the first term is just equal to x cubed, right? So Sn is equal to x cubed over 1 minus, okay, what's the common ratio? Well, the common ratio is x cubed over 7, right? X cubed over 7. And this is good. You don't need to simplify this any further. This is good enough. Okay, so we have done everything that the question asked us. We found the values of x for which that series will converge. And then we also found the sum of that series in terms of x. Okay, so that was the end of the problem solving video for part 1 of series. I hope you found all the practice we did helpful. Look at the second part for the rest of this unit. We're going to keep going more in depth about this stuff. And yeah, I'll see you then. Goodbye.